All right, sorry for starting a few minutes late. Okay. Okay, so today we'll be covering GAN. Okay, there's like two of you guys can just front row. I mean, there's like two people. You guys can just like sit up. Appreciate it. Vinny, what are you doing back there?
I'm about to dip it
Oh, you're staying for the lecture.
I'm not staying.
Oh my God. Okay, so generative models, right? So far, so in this case, when we talk about generative models, we're talking about like multi-dimensional data. So we're not really talking about the same, like about like generating a sequence the way like a RNN or transformer would. We're not really calling those generative models, right? So for our definition, if it can generate like a image, for example, that's like a generative model, right? So we'll be mostly talking about images, but really you could generalize this to like any multi-dimensional thing. So really the only generative model we've covered is a variational autoencoder. So if you don't really remember how these work, don't worry about it too much. We won't talk about them like, a lot. But before GANs were introduced, so GANs being generative adversarial networks, VAEs or variational autoencoders were the state of the art. And GANs, when they were introduced in 2014, kind of like blew them out of the water, right? So like they kind of ruled last decade as far as generative models go, and they're still pretty decent. Okay, so let's kind of think of just understand how these work, just the intuition. Let's think of our GAN wanting to generate the number eight, right? So the GAN works, it has two separate models. So it has the generator and the discriminator. So the goal of the generator is to just take like some one-dimensional noise vector, right? So literally a random vector. You could think of it as like, I like to say it's going from nothing to something. Like think of it like spontaneous generation. So we go from an input of just noise. It contains no meaningful information. And then well, at least we try to generate a image from that. So you can kind of make out a number eight. It's not super good, right? So after our generator does its best to generate a bunch of images, right? And then we give that set of images from our generator to something called a discriminator, right? So right now we have our data set of actual numbers of eight, right? Very nice, human drawn. And then we have the garbage from our generator, right? So the discriminator is literally just a CNN, right? It's just a binary classifier. That's all it is, just a binary classifier. And it learns each time the generator outputs like a set of images, it learns to distinguish between the generated images, the fake images, and the ones from the data set, the real ones, right? So in this case, it's pretty obvious, right? The discriminator can like train fairly quickly and figure out, okay, this is literally almost noise. These are well-structured images, right? But the idea, right, is once a discriminator learns the difference between like fake images and real images, right? The generator kind of uses its output as a form of feedback to make itself better, right? Okay, so let's kind of go through an example just to build the intuition up a little bit better, right? So let's say we want to be professional forgers, right? CS is not working out for us, right? So we want to forge Van Gogh paintings, right? Make them very, very like realistic. Problem is Van Gogh's dead, so we don't have some big brother model to teach us how to do it. Second problem is we're too broke to go to a museum, so we don't really have access to Van Gogh's paintings, right? So we did find a homeless art major on the street who was willing to learn the difference between your, trash drawings and Van Gogh's paintings, right? So in other words, we have our art appraiser that learns to identify, again, he's not an expert beforehand. He learns to identify the difference between your images and Van Gogh's. And you, the painter, who try to generate these new paintings in Van Gogh style. So first try, you have zero art skill. You have no idea what you're doing. You generate noise, right? Some M by N garbage. So just splatters on a canvas. So the art appraiser takes all of your images. Let's say you generate 10 images, all of your 10 garbage images, and then 10 of Van Gogh's paintings, and then trains himself to tell, okay, what's the difference between noise and a Van Gogh painting? You can imagine it's pretty easy for him, right? Maybe figure this out after like 10 days of training. Very, very easy for him, right? But the point is, right, what is he actually learning? I mean, learning the difference between noise and a painting isn't very hard. So maybe he just learns that, okay, paintings have paint on them, right? They have colors, they have distinct brush strokes, right? So that's all he learns because that's all he needs to learn, right? Does that make sense so far? Okay. So you then kind of work backwards from how he came to his decision. Again, all the appraiser knows is, okay, painting should have lines and they should have shades and colors, right? So we work backwards from his decision and then add shades and lines, right? And of course, you have a drawing now, right? But you forgot to use paint. You don't really have brush strokes. You don't really have any textures, right? But now the art appraiser has to learn to generate bad paintings or bad drawings, really, from paintings. So now he learns more detail, right? He learns, okay, Van Gogh uses paint, right? You know, he learns about his grading, stuff like that. Okay, again, the appraiser is done training, teaching himself, right? Now you go back to work, doing your best to fool him. And again, you work backwards from his critiques, right? Yeah, okay, so now you can actually generate images, or sorry, paintings, actual paintings, right? So now, this time around, the appraiser actually has a little bit more of a difficult job, right? Now he has to really learn what makes a Van Gogh painting a Van Gogh painting as opposed to an arbitrary one, right? So this is when he learns that fine grained detail. Now, as you may predict, once he learns his fine grained detail, you then work backwards and figure out, okay, a Van Gogh painting should have this texture, this art style, these brush strokes, and so on and so forth. So you end up generating an image that's exactly in the style of Van Gogh, but not a Van Gogh painting. So once you give it to him, right, he cannot tell the difference between an authentic painting from his data set and one of your images that look identical, not look identical, but look identical to the style. Okay. So tying this back to GANs, right? We have a generator that learns to generate images based off the discriminator's output, and it's never seen any of these images directly itself. All it does is gives its images to the generator, then works backwards to figure out how to make it better. And again, each time the generator gets better and outputs a data set for it, the discriminator learns to tell the difference each time. Again, we're not starting with the discriminator being an expert. It learns over time. Okay. So just some more observations. You might notice that they took turns training, right? So again, if we start with the discriminator here, right? It sampled a bunch of the generator's paintings, improved itself, waited for the generator to get better, and then resumed training once again. So they take turns training, and that includes forward pass and back prop. They go back and forth. Okay. So again, the loss function of a discriminator, it's not exactly this, but it's effectively binary cross entropy. And if you've never heard about this before, don't worry about it. It's just the standard go-to loss function for binary classification problems. Okay. So the generator's loss function is what really complicates this. And for now, just think of it as the inverse to the discriminator's gradient, right? So what is the discriminator's gradient? The discriminator's gradient for a certain image points in the direction of making the image better in a sense, right? Because if the discriminator is following its gradient, right, it's going down, 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 it's getting better and better at identifying, at telling apart the Van Gogh images, right? Now, if you take the opposite of that, well, you're learning how to make yours look more like the data set. So again, the generator's loss is proportional to the inverse of the discriminator's gradient. So again, the entire purpose of the generator is figuring out how to fool the discriminator. Okay. Yeah, I think this is a little bit of a review. Does this intuition make sense? Does anyone have any questions? Yeah.
Actually, things would those be the same every time the generator gets back with an image? It's with the things it's comparing to, like what it knows to be a real Van Gogh thing, but that would be the same.
You would randomly. So if you have a million Van Gogh paintings, right, you would sample 1,000. So they might not necessarily be the same each time.
The generator and just
Yeah. So in practice, you wouldn't really sample the same known images to prevent overfitting, but I mean you could, right? But yeah.
So when you say proportional, do you mean is it directly getting its loss from the gradient, or is it just informed?
Sorry, proportional. It is proportional. You can just think of it as it wants to maximize the discriminator's loss, right? So the discriminator's gradient tells it in what direction to go.
Okay.
That makes sense. We go over this in I cover the actual loss function a lot more depth.
Okay, got it.
But for now, the generator wants to make maximize the discriminator's loss, and the discriminator's gradient tells it how to do that. Okay. So if we were to actually build out this GAN model, so again, we have a discriminator model and then a separate painter generator model. Well, building it is actually very straightforward, right? So if we talk about the discriminator, again, it's literally just a CNN, right? We have a tan H layer. So we output numbers from 0 to 1, right? 0 being, okay, this is fake, 1 being this is a real image, or the inverse, doesn't really matter. Okay. The generator might look a little bit more unfamiliar, but if you were there for the variational autoencoder lecture, this is a like the decoder of a autoencoder, right? So the idea is we take like a small little one-dimensional vector, and again, for those of you that just joined, the idea of a generator is that it spontaneously generates images, right? So we're trying to generate an image from like noise, from nothing to something. The input contains no useful information. Despite that, we want to like create information. Again, we're spontaneously generating stuff. So the input is just some randomly sampled one-dimensional noisy vector. And then we then learn something called a transposed convolution, and we just feed those through nonlinear layers. So a transposed convolution is, you can think of it almost as the inverse of a convolution. So you take some, n by n portion of your image, and then you take a kernel, not necessarily the same size, or sorry, yeah, of the same size. And then using the kernel, you're able to kind of blow up the image, like increase the size of the image. So from two to 2, you went to like, you added 1 on the width and the height, right? And again, this kernel is a learnable weight, right? So think of it as learning to add detail to an image and increasing the size. So that's how we can go from like a 1 by 10, for example, vector. It's usually by 1 by 100 though, to something that's like 256 by 256. Okay. So are we kind of good on the intuition behind a GAN? So they alternate the generator trying to fill the discriminator. They take turns training, right? And the model architecture is mostly stuff we've seen before. Okay, so to really get a actual understanding of GANs beyond the intuition, we actually have to take a lot of steps backwards and ask ourselves, what is a data set? Okay, so let's just kind of forget what we know about like the basics of machine learning for a second. And let's say we want to construct a data set of numbers, right? Just any number, any hand-drawn number, numbers on sign, so on and so forth. Right? Well, if I gave you all the images in the known universe, right, you'd pretty easily be able to tell me, okay, that's a number, that's not a number, that's not a number, so on and so forth, right? Very easily. So let's say we kind of wanted to visualize this like on a graph, right? So on the x-axis, we have all possible permutations of n by n in the universe, all conceivable images that could possibly exist, right? And then on the y-axis is just, a peak if that image is a number, 0 if that's not a number, right? Okay, so this distribution represents if we want this in our data set, like if we want some generator to pluck something from this, right? So again, if we want a generator that could generate images, right? Well, we would want it to pick an image of a number, right? As opposed to an image of like a cat or something, right? Now, obviously, there's no conceivable way. Oh, yeah, sorry. Before that, we can kind of think of this like graph as a probability distribution, right? Where a positive probability means, okay, this is like an image we want our generator to output, and a probability of 0 being, okay, this is like something we don't want. As you may remember with probability distributions, they sum up to like 1. So if there's only 3 conceivable images of numbers in the universe, 5, 8, and 7, each of those will have a probability of 1/3. Does that make sense? Okay, and there's no such thing as a negative probability. Okay. Now, of course, we cannot actually get this distribution, right? Because we don't have all known images in the universe, right? So instead, we get a sample, we get a subset of that, right? So maybe 250 images that you draw yourself, right? So the hope is that that sample of 250 images, that distribution, roughly approximates the distribution of all numbers in the universe, right? And so we call that like approximation, that subset, a data set, right? And again, the hope is that this data set, P data, approximates the global kind of world distribution of all images of numbers P. Make sense so far? Okay. All right, so I'm going to introduce one more distribution. That should be P of G, P generator, not P data. I'm going to introduce one more distribution, which is P of G, right? So if P is all the distribution of all conceivable images, P data is an approximation of that. P of G, P generator, should be all possible images our generator can output. Now, intuitively, we want P of G to match P data, right? Well, really, we want it to match like P of G to match P, but that's really hard, right? Because P of data is an approximation of P. So we'll satisfy ourselves with an approximation of P of data, right? And so this is kind of the intuition behind like all generators kind of follow this probabilistic idea, right? Of, okay, so we can kind of visualize like the images we want on, this continuous distribution, and a generator should pluck things from that distribution, right? Now, what's important to know is that this distribution is continuous, right? So in other words, this distribution should include images that are not in our data set. So in other words, if our data set only has 250 images, well, we still want images that look like stuff in our data set, but might not necessarily be in it. Does that gap make sense? So in other words, like if you kind of pick the space between 5 and 8, like this arbitrary point, that might not correspond, like that should, like sampling from that should yield you an image, even if that image is not in the data set necessarily. Okay. Okay, so again, we want our PG, the probability distribution of a generator, to match P data, right? And so there's kind of two ways we could go about having P of G match P data, right? First way is directly trying to learn the P data distribution, right? So we take stuff from our data set, right? And we learn to say, okay, that number should have, 0.3, that should be 0.3 probability, that should be 0.3 probability, and go on for all, 3 images in our data set, I guess, right? And so variational autoencoders kind of follow that intuition. Now, I'm not going to go through the math, but that kind of involves you trying to solve the, like, calculating the area under the curve of this probability distribution. And that's an intractable problem, meaning like you can't solve it, right? So VAEs get around this by trying to approximate this. But that approximation oftentimes yields to a lot of problems. So like pre-GANs, VAEs yielded very like blurry images, right? So you might have an image of a 5, but they're kind of blurry, right? So they got pretty close. What a GAN does is trying to implicitly learn this, right? So it never sees this data. So in the data set, instead, it tries to guess which images should be on this distribution, right? So again, it tries to produce images that it hasn't seen before. It's never seen the data set, but it's like, hey, okay, I think this new image that I made up should belong here. So in that way, it's able to approximate P data. So again, the whole argument of a GAN is that the second way of trying to like guess and check your way to approximating P data, as opposed to directly trying to solve for it, is a better way of approximating P data. Does that distribution make sense? It's a little bit abstract. If not, don't worry about it too much. We won't be talking about VAEs after this. Okay. So again, the hope is that the generator we output is somewhere like corresponds to a peak in our distribution, right? Even if it's never seen that image in the data set before. And this is only possible because we assume that the discriminator is able to learn what is and is not a part of the distribution, right? So again, the discriminator could be like, okay, if we sample anything from here, after a little bit of training, it could be like, okay, this is not part of the distribution, but stuff sampled from here definitely is. Okay. Okay. So now we have to kind of ask ourselves, what is a ground truth, right? So again, this is also we've seen before, it's just written a bit more complexly. Okay. So again, remember our discriminator really has 2 classes, real or fake, but really, is this from the discriminator or is this from the data set, right? 2 classes. Okay. So if an image, I'm going to, for now on, whenever I refer to X, I mean an image. So if an image X is from P of G, so from the generated, the distribution of the generator, it's fake, so the discriminator should output a 0. If it's from the distribution of the data set, then it's real. The discriminator should output a 1, right? So what's the probability of the label, or I guess, so, you know, again, we're talking about ground truth here. So the label of the label being 1, if the distribution, sorry, if you, what's the probability the ground truth being 1 if we sample an image from the generated data, PPG? It's not really a probability, it's a yes or no question. We sample an image from P of G, is it real or not? No, right? So if we were to kind of write this, so we have 4 cases, right? What's the probability of us labeling something real that's fake, something that's labeling something that's real as real, something that's fake as real, and so on and so forth. Right? 4 cases. Okay. So if you just want to write this out more formally, have you all taken prob? All of you? I think VLs hasn't, so I'll break this down a little bit more. All right, so you guys should have seen the conditional probability sign before, right? That's what that pipe is supposed to be, right? So if an image is from P of G, what's the probability of its label being 1? Well, that should be 1, that should be 0. Like, again, these aren't continuous values, right? It's a 1 or 0, 0, 1, right? So again, this is literally just same thing as manually labeling a data set, but we're just thinking of this as a probability distribution for now. Okay. So that's because the discriminator's output more closely follows, like, is more intuitively a probability distribution, right? So in other words, the discriminator should output a 1 if it thinks the image is real, should output a 0 if it thinks the image is fake, right? So yeah. And so what we want is the probability distribution of the discriminator's outputs to match that of the ground truth, right? So just as how we wanted the generator's distribution to match the distribution of the data set, so P of G equals P of data, we want P of D, the discriminator, to match the distribution of P of C, the ground truth. Okay. So the question is, how do we check if 2 distributions are equal? Like, how do we even know, like, how close they are? Does anyone remember this? Kind of spoil on the next slide. All right, I covered it once, so don't worry about it. It's called the KL divergence, or the Kullback-Leibler divergence. Okay, so just given 2 probability distributions, so for example, P and Q, right? We can compute how similar or how different they are, right? And yeah, so again, this metric will always be positive. There's a proof for that, but just for now, just assume it'll always be positive. Okay. And what we're doing here is for every sample in our data set, so for every possible X or for every possible label, right? We just take the log probability, or sorry, the difference in, we take the log of their differences and multiply that by the probability of the, of it being the ground truth, right? So what does that mean? Little Desmos here. Okay, should just be the next slide. Okay, so here is a graph of log X, right? Okay, so let's say, make sure I remember. Okay, so the numerator is the probability of a, is the probability distribution of the ground truth. The denominator is that of the discriminator, right? So if for a given image, right, the ground truth is like, okay, that's definitely a real image, right? Because again, the ground truth can only be 0 or 1. Okay, so that is definitely an image, right? Well, if the generator is like pretty bad, and it's like it's pretty confident that that's not an image, well, you can see that the KL divergence for that single term, right, is 0.7, right? And the more far off the discriminator gets, the higher that KL divergence term goes, right? Does that make sense? Okay, and again, if you were to flip this, so the discriminator is sure it's, I mean, that just comes undefined, yeah. because this would just be 0, right? 0 over something 0. So log of something becomes undefined. In practice, we would just sub this out with a 0, right? Okay. But yeah. So yeah, so we're kind of checking at every single data point, like that divergence, and then we just take the sum of all those terms. Does that make sense? Okay. Was the Desmos thing useful, or was it clear from just the equation?
I think that was helpful.
Okay, appreciate that. So again, it's a summation because we have discrete number of images, and so we're taking the sum across all images. You could also, KL divergence also has like a continuous counterpart that's an integral, but we're not really worrying about that. Okay. And so what we want, right? So the loss of the discriminator is this KL divergence, right? So the difference in distribution between, between like the ground truth distribution and its distribution, the distribution of discriminator. And so if those two distributions like are the exact same, that means that the discriminator has now learned the ground truth. In other words, it has a perfect classification accuracy. Okay. So here's some math. I'm not going to get into that. It's here in case you're interested, right? But this summation simplifies to these two separate terms, right? So ignore the, are you guys familiar with expectations? Okay, if not, just ignore them from now, right? So for a given image X, right? We want to, so again, this is the loss, right? So we want to minimize this. So it's related to the log of dx, right? Sorry, if we sample an image from the data set, right? Again, we want to minimize this term, right? So if we increase d of x, this term gets minimized, right? So in other words, if we sample an image from the data set, we want d of x to equal 1. If we sample an image from the generated data set, right? We want this. So we want to minimize. So 1 minus d of x will be minimized if d of x is equal to, it's equal to 0. Okay, so again, this literally just corresponds to our labels, right? We want it to equal 1 if it's a real data, if it's a real image, 0 if it's not, right? Straight from the labels. So coincidentally, this formula is also identical to that of binary cross entropy. So remember how I said like the discriminator's loss function is pretty much like binary cross entropy? Well, the KL divergence pretty much simplifies to that. So the expectation is just telling you to take the average across all images, right? So you have 10 images, we're just taking the average across those log probabilities. Okay. So is everyone kind of clear on the intuition behind the discriminator? So if we minimize this, the two distributions align with each other, and the discriminator has learned the ground truth. Okay. So I kind of just explained this. Oh yeah, just little math thing. Why do we have the negative signs here? Exactly. Because d of x will always be a probability, right? Between 0 and 1, which means it'll always be negative. Okay. So yeah. Okay. So now we're almost at the GAN loss, right? Very, very close. But again, the discriminator and generator are trained separately. And we just went over the discriminator loss, right? So that's what that is up here. But remember, the image X, right, is sampled from P of G. And if it's sampled from P of G, that means the generator generated, right? So really, when we say D of X in this right-hand side, we mean G of Z. And Z is that like noise vector we sampled, that noisy garbage vector we sampled earlier, right? So Z is the input of the generator, right? So this right-hand term is equivalent to this right-hand term. Does the conversion here make sense? Okay. And so what the generator wants to do, remember, it wants to fool the discriminator, right? So in other words, it wants to minimize the discriminator's, maximize the discriminator's loss function, right? But again, we're doing gradient descent. So that means minimizing the discriminator's, confusing myself, the negative of the objective for the discriminator. So if you simplify that, that just simplifies to the right-hand side. right? So in other words, they have mirrored loss functions, right? Can anyone actually try to guess why this left-hand side disappears for the generator's loss? Yeah, pretty much, right? The loss is, with this ends up just becoming a constant, right? So if we take the gradient of this entire term with respect to the generator, well, that just always goes to 0, right? So there's no point, like we could include that, right? But it'll always go to 0 in back propagation. There's no point in including this. Yeah, correct. Okay. But again, it goes back to the generator trying to fool the discriminator. They have inverse loss functions. Okay. So we can actually kind of structure this as in the context of game theory, where you have two players, like D and we'll just call them players D and players G. And again, player D is trying to maximize its value function, right? And player G is trying to minimize player D's value function, right? So in other words, from player G's perspective, if D is doing really bad, then it's winning, right? So take like tic-tac-toe, for example, right? You play a finite number, you play 10 games, right? If you are player D, right, and you score, each time you score a point, you either win a game +1 or you lose a game -1, right? So if player D wins 6 games and loses 3, then the score is, well, the relative score is, -3G, D is, +3D, right? Okay. So again, so if V is the number of games won, right? Then, how well G is doing is really just the inverse of how well, or sorry, the opposite of how well D is doing, right? Does that make sense? Okay. Yeah, so G wants Z to have a more negative score, D wants a more positive score. And again, the score in this case is just that value function. In the context of GANs, right? V is this value, right? So you'll notice it's positive, right? So again, the discriminator is trying to maximize this, right? And in turn, the generator is trying to minimize this. Okay. So remember, if you remember, they take turns, like it's not like they're trying to like update their strategies at once. So the generator makes its changes, takes a break, the discriminator makes its changes, takes a break, and so on and so forth. Okay. Yeah. Okay. So here's kind of a visualization that they used in their paper, or like an adaptation of it. I'm going to like break it down, right? So again, we have this orange guy, and that's P data, right? We've seen this P data before. What we want this P of G all the way over here, right? To be aligned with P data, right? So again, P data has spikes where there are MNIST images or just hand-drawn images, right? But right now, P of G is only spiking where there is noisy stuff, right? So we want to shift this distribution to, we actually want to split it to fit to these peaks, right? So, okay. So the discriminator is kind of doing its own thing, right? So remember, this is a probability distribution. So at this point, right, the discriminator is like roughly 0.4% sure this is a real image. And at this point, it's like, 0%. It's pretty sure that's a fake image. But right now, neither one of these have trained. So they're just outputting garbage, right? So once, we start training, the discriminator will look more like this, right? So if you sample anything like from the image, or sorry, from the, from P data, it will give you something close to 1, right? Now, if you sample anything from P of G, it'll give you something close to 0. But remember, P data, the discriminator is only looking at images from P data and P of G, right? So it's not really improving its behavior on this left-hand side or the center side, right? But again, as it is now, right, it's anything that's P of G is being classified as 0. Anything that's P of data is classified that's pretty close to 1. So it's doing a really good job, right? Now, P of G, it's the generator's turn to train. It's now able to shift its distribution. So it splits into 2, right? One side moves closer to that data. Like it hasn't fully fit to it, but it's a lot closer to it, right? More importantly, it's in the range where P of data thinks it's a real image, right? So again, if we sample something at this peak, right? Well, that corresponds to a score of like what, 0.8 from P of data? Sorry, 0.8 from the discriminator, right? So again, we're still like, if you actually look at the image we're taking, it's still pretty bad, right? It's still like pretty noisy. But from the discriminator's perspective, it hasn't learned that difference. All it can tell is the difference between noise and an actual image. Okay, so once again, right, the generator finishes training. This is P of G. We now improve P of D, the discriminator's ground truth approximation once again, right? So you can see, if we sample like one of those fake images, that has a pretty low probability, right? And, if you sample something from here, it still has a low probability. But, it's confused at this point, right? So at this point, it's pretty much 0.5. That's because any image taken from the generator, so from that blue section, right, looks almost as if it's taken from the data, P of data. So at that point, it's confused. It has no idea what to do. So you keep going back and forth. So let's say at epoch 100, the generator's distribution almost perfectly fits the P of data's distribution.
Why does it go down to 0.5 for the, like the pink, like shouldn't that still be 1 for?
Yeah. So first, if we were to sample an image from this, like, from P of data or P of G, we would not be able to tell the difference like at all. They look like the same image.
Oh, so it's like, it only has a 50% chance about which one it is.
Yeah, 0.5 means it has no idea.
Okay,
Like it's literally taking a guess.
yeah,
So
it knows that stuff outside of that is definitely not, but inside of that, it has no idea.
for this example, yes, right? Because remember, we have never sampled an image from here. We just kind of, that's actually a little bit misleading. Like, from where P of, like, we have been here in, like, I think here before P of G, right? So anywhere P of G was before, so like the noisy places, it knows for certain those regions, should have a probability of 0. Places where, P of G has never been before, like this left-hand side, it has no idea about. But at least if we were to only sample from P of D, P of data, and P of G, it would always give you 0.5. So again, anywhere you would sample from on P of G, it would give you a probability of 0.5. Does that make sense? Did I lose anyone in that? I know it's like kind of confusing with like 3 lines and stuff. You good? Okay. We will see this example again. So if you have any questions, just let me know. Okay. So again, GANs are able to approximate this P of data just by guessing and checking, right? And so again, they're very, very powerful, right? GAN models like 10 years, like 5 to 10 years ago, just completely blew out VAEs, which directly try to approximate P of data. But as you can maybe kind of have inferred by now, they're really, really hard to train, right? So I've kind of isolated the 3 most common problems, but they have some other ones, right? So first is that the discriminator can be really finicky. If the discriminator is too good, that's bad for training. If it's like really bad, that's obviously bad for training as well. This idea of the min-max game, right? Of, where you're both trying to, like of this problem setup, that's not guaranteed to converge theoretically. It is in some cases, not always. So that impacts GAN training as well. And then the most famous problem that GANs have is something called mode collapse. Okay, so first, what do I mean? So between the difference between the optimal and the best possible classifier. So if we think about the best possible classifier, that is a classifier that can, like, that has perfectly fit to the ground truth, right? So no matter how realistic your generated images look like, it'll always be able to tell the difference, right? No matter what. So let's say the generator is perfect, right? It's only outputting 0s and 1s in the right places. Well, anyone have any guesses to what happens to the loss of G? So the loss of the generator, and more importantly, what happens to its gradients? All right. So if if the generator is perfect, right?
0 loss.
For the generator?
For the discriminator.
Oh,
the
yeah,
loss
yeah.
would be 0, but then that would mean the loss would also be 0 for the generator.
The more important thing is that it reduces to some constant, right? So in other words, right? Yeah, so I think in some cases it is 0. Yeah, I think so. Okay. Wait, no, it would be undefined, right? Never mind. Okay. It would reduce to some constant, right? So effectively 0. But what that means though, right, is no matter how you change your generated image, like if you make it worse, if you make it better, right? Your loss will always be the same thing, effectively 0, right? What that means, if your loss is a constant, what does that mean about your gradient? Your gradients become 0. Yeah. So your gradients effectively vanish. So if your generator becomes too good, or sorry, if your discriminator becomes too good, the gradients of your generator effectively vanish, right? So this can happen even if the discriminator doesn't really learn that ground truth, right? For example, if you remember like the painting example, right? If it goes from like learning the difference between like, I don't know, like if it learns how to like identify like a Van Gogh painting, right? And then you give it some crudely drawn image, that would still get like a lot, like that would still be the same loss relative to like a noisy painting, right? So in other words, the drawer like gets no useful information. Okay. So in other words, we can't let our discriminator get too good during training, right? So the optimal like behavior of the discriminator is that it actually never learns that ground truth, right? So as Seth pointed out earlier, the optimal discriminator reduces to like 0.5, right? So if you have the same number of generated images, P of G, or samples in P of G, the same number of images in your data set, so 5 in your data set, 5 generated, this should reduce to like half, 0.5, right? So again, an output of 0.5 means your discriminator has no idea about the difference between the real and generated images. And again, we only want this to happen if we assume that the generator is perfect, right? So again, if the generator is like near perfect, and this is the behavior we're getting, we can still like train from this, we can still calculate gradients from this. But if the generator is like getting pretty good, and then suddenly the discriminator becomes perfect, then our gradients vanish. Okay. So how do we mitigate this? We've actually already discussed the solution for the most part, right? While you're alternating training, you just have to stop the discriminator like fairly early. So in practice, if you just stop after like k steps, as long as k is not like something really unreasonable, like 1,000,000 or something, right? You really just want the CNN to not overfit, right? To not memorize that training data set. So as long as the CNN is not overfitting, you're fine. Just stop after like k epochs. The other thing, right? So we're talking about the case where the discriminator is really good. If the discriminator is really bad, right? Then we're not really, like the generator assumes that the discriminator can tell the difference between real and fake, right? If the discriminator sucks at doing that, then the generator is like not learning anything useful, right? So while we want to like stop a little bit early to prevent the discriminator from getting too good, we still want the discriminator to be further ahead of its training than the generator is. So for that reason, we have the learning rate of the discriminator usually higher than that of the discriminator. We have the learning rate of the discriminator higher than that of the generator, right? So the discriminator is always like a little bit better at classifying than the generator is at generating images. But we don't want it to get too good and overfit to the data set. Does that distinction make sense? Okay, so that was a pretty easy to address problem. The second more complex one is that the min-max game could just possibly never converge, right? So think of like rock, paper, scissors, right? Let's say player 1 starts with the strategy of always going rock. Player 2 just starts with always going scissors, just randomly initialized strategies, right? Well, player 2 after the first game is like, okay, rock is weak against paper. I'm going to switch to paper, right? They play a game. Player 1 loses this time, right? Okay, player 1's seeing this, right? Now it's player 1's turn to change a strategy. So it goes to scissors, right? It wins the game because player 2 is fixed at paper. And now player 2 is like, okay, rock beats scissors. Now you see we've kind of like, we're back at square one, just flipped, right? So we're going to keep cycling through these possibilities. In other words, this min-max game, right, never converges, right? Does this make sense, by the way? Okay. So again, before we were assuming, like with GANs, the min-max game, like we hope it reaches an equilibrium, right? There are cases in which it doesn't. Here is an example. Okay, this is very messy. Look at these first two graphs, right? So the first graph, so we're on epoch 0 or epoch 1, I guess, right? After you generate updates, right? Let's say it makes instead of making a gradual update, like just slowly shifting distribution, the gradient is very large. So that distribution moves all the way to this left-hand side, right? So now, so again, the discriminator hasn't trained yet. So now we train the discriminator and it learns, okay, stuff on this left-hand region is fake, obviously. It doesn't bother updating anything on the right-hand side. Does that make sense? Okay, so once again, the generator, let's say it gets a really big gradient, right? It makes another really big jump to the left-hand side, right? Okay, the generator is like, okay, I'm just gonna, squash those probabilities. Well, let's, hypothetically, again, all this stuff is just uninitialized random behavior from the discriminator. So you can kind of see the generator can keep kind of moving in that left direction. And the generator can keep squashing it and then by accident, encouraging the generator to move in that direction, right? Because again, the generator is just trying to move in a direction in which the discriminator fails to detect it as fake. So it could just as easily move to the left, right? And so this game will never converge. The generator was, this left-hand side has like infinite space. Let's just keep running away that way. So if we get unlucky in how we initialize our weights, right? And more importantly, if our gradients are too big and our generator is like jumping from, here to here, or like from this left-hand side all the way to the right-hand side, right? It could be the case that our model never converges. Okay, so this is usually addressed just by having, initializing your weights, just, not completely randomly. And more importantly, just normalizing your gradients. Generally, if you can normalize your gradients fairly well, this problem is avoided. But again, it's not a very that's a little bit of a hand-wavy explanation. There's a bunch of papers on how to try to figure out this problem. So this problem directly leads to the famous mode collapse problem of GANs, right? So again, if we're looking at P data, right, it has peaks everywhere where there's an image from the data set, right? So maybe this peak corresponds to an image of 5, that of a 3, that of a 4, so on and so forth, right? So what could be the case is that our generator only learns one of these peaks, but it learns that peak really, really well, right? So in other words, no matter what noisy vector we input into the generator, it will always output effectively the same image, right? So for example, it'll always output the image of a 3, right? And from the discriminator's perspective, well, it can't tell the difference between a real 3 and a fake 3, right? And from the generator's perspective, it's outsmarted the discriminator. So oftentimes you just end training with your generator only able to output a single type of image, right? So it's not really quite overfitting, right? It's mode collapse is its own problem. But does this make sense? So the reason why we call this a mode is we have a mode, like a peak. So a mode corresponds to everywhere where there's a peak. So we only learn one peak, which corresponds to one type of image. Oftentimes just one singular image. Okay. So one solution, a fairly common solution, is called mini batch discrimination, right? So again, all of these blue guys, so we have the same discriminator, we feed it 4 separate outputs, generator. Again, because the generator has mode collapse, it just keeps outputting the exact same image, right? But again, the input to the generator was different each time, right? So we pass to the CNN, right? Our final our final intermediate values before we pass it to the 10H and then linear layer is, we have them here. I know it's a little bit hard to see, but these values kind of look very similar. These intermediate values, right before the last layer, they fairly look close. We have 0.1 minus 0.8. Up here is 0.12 minus 0.8, right? They're all very close. So the solution with mini-match discrimination to encourage diversity amongst our outputs is to add this diversity term, right? So we take that intermediate output right before our output layer, and we concatenate this diversity vector. So we don't change anything from the CNN. Instead, we just add stuff to it, right? And the hope is that this diversity vector contains enough information such that the discriminator, just from looking at this, is able to tell like, hey, this might be a fake image. So I'll explain what that means after going through the example. Okay. So the way we compute this diversity vector is first we take all of those, final, like pre-final layer outputs, right, from all of those fake images that we just produced, and we feed them into this transformation matrix T, right? T is learned, but it's not a neuron, right? It's just a single transformation matrix. If you've taken linear algebra before, or if you remember the transformers lecture, T effectively learns to bring all of these really vectors into the same vector space, right? What that really means is like, what we want to do is compute the distance between each of these vectors in the next step, just to see how similar they are. They might not be in the same vector space to do so. So T makes sure that they are, right? So oftentimes T might just be the identity matrix. It might not really do much. It's just in the case that these intermediate vectors, like, happen to be in separate vector spaces. Okay, so if that didn't really make too much sense, just kind of imagine that these values all look the same because they come from visually similar images. Okay, so we then compute the distances between them, right? So the distance, if you were to plot them on vector space, right, their vectors are all pointing in very similar directions. Again, if you're not good with vectors, that really just means that the values at each elements are very close together, right? So if you can see this, 0.1 minus 0.1, 0.8 minus 1. Okay, that's not a good example. 0.1, 0.1 minus 0.8, 0.8, 1.1. Like they barely differ, right? So in that case, the distance would be very low, right? Okay, so if we're thinking about generating the diversity vector for this first guy, we calculate the distance for each of the other images in its batch. So in this case, we have a batch size of 4. And we then take a weighted sum between the distance of the other vectors, and we just add them together, and that's how we get our diversity vector, right? Now, if all of these images look very similar, right, the idea is that their diversity vectors will all look the same as well, right? So one assumption we're making is that our dataset images all look visually different, right? Or different enough, right? So again, mode collapse is effectively when you're outputting the same type of image. In the case of MNIST, you're outputting the exact same image, right? So you're only outputting the same number of this, like, image of this 5. You're not even outputting variations of this 5, right? So their diversity vectors of all fake images are very, very close together, right? Whereas the diversity vectors of of the data set all look completely different, right? From the model's perspective, it could then learn that, hey, like all of these fake images, the last, let's say 2 elements all look very, very close together, right? So it learns, okay, if the last 2 elements are 1.0 and 0.4 or near that, I won't even bother looking at this stuff. I'll penalize these as, or I'll classify these as being fake, right? And again, the real images don't have that trend.
The real images also have the diversity vector.
Yes,
So
yes.
it's because their batches are different, like there'll be like a 1 through 10 in their batch, that like their diversity vector will be different.
Sort of. It's more so that the images will just look different. Like the real images, right?
Yeah.
It's not like our data set only consists of the same image, right? But the outputted fake images all look almost the exact same. Right? Although you are right. Just because the images are visually similar, if they're from different batches, their diversity vectors will be totally different. So if they're in the same batch and they're visually similar, then their diversity vectors will be very similar. Does that make sense?
Yeah.
Okay. So again, yeah, any questions about this diversity vector? So in the case that mode collapse is not happening and we're generating authentic different images, these last 2 elements or these last k elements will all look completely different. the model usually interprets it as just like noisy stuff it ignores, right? Okay, so these diversity terms really only kick in when mode collapse happens. Okay, so that's pretty much it for GANs. So far we've really only covered like the original GAN paper. Mode collapse, I think, sorry, the mini batch stuff was a little bit afterwards, but this is just the straight up like the standard GAN model. A WGAN or Wasserstein, I think, Wasserstein GAN, I think that's how you say it, was proposed pretty quickly after. And so its kind of fundamental improvement is that instead of the discriminator outputting a probability, so 0 to 1, it outputs just a scalar called, I think it's like the earth moving value. It's a pretty dramatic name. But the point is that value is not restricted to being 0.1 or 0 to 0.1. And it just so happens to be a better metric compared to just a probability distribution. More importantly, not more important, but that also entails that the gradients just so happen to end up being clipped, right? So remember, like when we had that example of the P of G just running away to the left-hand side because of the large gradient updates. Well, if the gradients are forced to be small, then that probably won't happen. Okay, so two other GANs that were way after that were style GAN and cycle GAN. So these both produce a lot of pretty prob heavy changes. But once these two were posed, that's when GANs really start to start blowing away benchmarks, especially cycle GAN. As you can kind of see down here, one kind of common thing that cycle GAN had in its paper was like kind of taking an image and changing like the environment of it. So going from an image of a zebra and then just almost adding, it's effectively adding a filter. So going from an image of a zebra to an image of a horse. That was just like a pretty cool thing that cycle GAN. But yeah, okay. So that's it for the GAN paper, or sorry, GAN presentation. Next week we'll be covering diffusion models, right? So far we've learned VAEs, although that was a long time ago. So far we've only learned GANs for generative modeling. Next week we'll be covering diffusion models, and that's kind of been the huge model outside of transformers, I guess, of like the last 5 or so years. But yeah, okay. Thank you guys for coming. As always, if you have any questions, feel free to stay back and ask away. Oh.